Next, we talk about a very important concept in graph theory, namely graph isomorphism. An isomorphism of two graphs G and H with this set of vertices and edges is a bijection. So an isomorphism is actually a function, right, or a mapping from the vertex set of one graph to the vertex set of another, such that any two vertices u and v in the vertex set of the first graph are adjacent in G if and only if the vertices they are mapped through the isomorphism are adjacent in the second graph. Okay, so this definition is a mathematical definition, but it might be a little bit confusing. In essence, what we say here is you have two graphs, and then isomorphism means that a function where you map each vertex of the first graph to another vertex in the second graph so that the structure of the graph is exactly the same. The structure is preserved. Okay, and a special case, if the two graphs G and H are the same graph, that means you have like a permutation of the vertices, and then that preserves the structure. In this case, we call this isomorphism an automorphism. Like, for instance, you have a very simple graph here, let's say u1 and u2, and an edge between them. If your function, your bijection is defined as f of u1 equals u2 and f of u2 equals u1, you see this is an automorphism because if you switch the nodes, then the structure is preserved, and therefore this is an automorphism. But let's look at this example. Here you see a complete graph with four vertices, and these are represented by K4, such graphs. For instance, the complete graph with n vertices is K sub n. A complete graph means you have an edge between every pair of vertices in the vertex set. So K4 is given here, the complete graph with four vertices. And when you look at this graph on the right-hand side, you see that when you map A to U, B to W, C to Z, and D to V, you preserve the relationships or the edges, let's say, between each pair of vertices. So A and B are neighbors. Similarly, U and W are neighbors too. D and B are neighbors. Similarly, W and V are neighbors too. Obviously, the two sets should have the exact same number of vertices and the exact same number of edges, which is the case here. But clearly, that is not the only property that these share, and that's not sufficient to conclude two given graphs are isomorphic. And that's an important problem, and we have many algorithms for detecting isomorphism between two given graphs. And best algorithms known for determining whether two graphs are isomorphic or not have exponential worst case complexity in the number of vertices. But when you look at the average case, we have a number of algorithms that have linear complexity. So that's a good news. In the general case, for general types of graphs, this is a significant problem, graph isomorphism problem, in that we do not really know whether this problem is NP complete or a polynomial time problem. So it's unknown in which class it falls. We obviously know it's in NP, but we do not know whether it falls into the class of NP complete or the class of P. So since, if you remember, we do not know whether P equals NP, we also do not know whether there exists an intermediate class, NP intermediate, the class of problems neither in NP complete nor in P. So if P and NP are indeed distinct, or maybe not distinct, but not equal, let's say, in this case, we would have a class of NP intermediate, and graph isomorphism would fall into that category, or let's say could fall into that category. But as it stands, we do not really know in which class it belongs beyond NP. So we are not sure if it is NP complete, we are not sure if it is P, and therefore we cannot really gauge its complexity as of today. But we have polynomial time algorithms. We also have some linear time algorithms for detecting special types of, detecting isomorphism in special types of graphs, such as trees, for instance, complete graphs, or some special types of graphs. We have certain algorithms that are very efficient. So in practice, if your graphs do not really have very arbitrary structures, most of the cases we have efficient algorithms for detecting graph isomorphism between two given graphs.